The logical place to start with these lessons is by defining what deep learning is. In some ways, I can do that very simply. Deep learning involves stacking these straightforward little algorithms called artificial neurons together to solve problems. That simple definition, however, doesn't do justice to the elegance of deep learning. To develop an intuitive understanding of how deep learning is so powerful and why it's so relevant today across so many applications, we're going to discuss a particular application of deep learning, which is to machine vision. Vision on Earth began 543 million years ago when trilobites developed a rudimentary visual system. This was really important. It began the Cambrian explosion in species diversity. So we went from having a handful of classes of species 500 million years ago to the thousands of classes of species that we have today, thanks to vision. And this makes sense because once trilobites had vision, they could see at a distance. They could see mates, they could see food, and they could see predators. So that meant that their predators needed to evolve as well to keep pace, and so on and so on. So the visual system developed across many different species, and fast forwarding ahead quite a bit to today's mammals, we jump all the way to 1959 when some Harvard postdocs named Hubel and Wiesel were doing experiments on the cat visual system. So they were recording from single neurons in the visual cortex of the cat brain, which, just like in humans, is the first part of your brain to get a signal from your eyes. And they were showing pictures to these cats of fish and cats and dogs and complex images, expecting that to cause brain cells to fire in the primary visual cortex. But they weren't getting any good readings. Then one day, as they removed a slide, they made the serendipitous discovery that on one of the slides they were showing them, there was this dark edge, and that dark edge caused some neurons in the primary visual cortex to fire. So their serendipitous discovery was that these individual brain cells in the visual cortex were responding to bars at very specific orientations. We know today that this is how the mammal brain works in general, and it's how it works in humans. So this primary visual cortex, receiving connections directly from your eyes, is doing very simple computations. It's really just detecting the orientation of edges. Then these first visual centers pass information up into later centers in the brain, where those edges are recombined into slightly more complex features like corners. And then higher up, those corners and simple shapes can be recombined into increasingly complex representations like roofs and houses, wheels, and faces. In humans, in fact, we have an area called the fusiform face area that is specialized to distinguish the faces of individual people. Now, in 1980, a guy named Fukushima proposed an idea called the neurocognitron. And what I have here on the left is our timeline of biological vision up to today. And over here is a machine vision. So we have this one path on the left that I'm going to start explaining first. So Fukushima here in 1980 proposed this neurocognitron inspired by the biological idea that we should be able to create increasingly complex representations, just like Hubel and Wiesel were seeing in their research on cats. In fact, in this diagram from the Fukushima paper, you can see that he references Hubel and Wiesel specifically. So he talks about how the mammalian brain has these cells doing simple computations like recognizing edges and building those up into more complex representations, simple shapes, and higher complexities until he proposes this idea of a grandmother cell that fires only when you see your grandmother. So this same kind of architecture is what Fukushima proposed for machine vision, having layers of hierarchy that are building up increasingly complex representations. So that kind of idea of biologically inspired, complex representations being learned hierarchically is happening here on the left. Fast forward a little bit further to 1998, Jan LeCun and his team at AT&T Bell Labs had refined Fukushima's idea further, and they created a commercialized zip code reader. So we're actually going to build the network that they built, called Learning15m, to classify zip code digits in these live lessons. And what you'll notice is that this has the same kind of idea of gradually building up complexity in neurons. So if you have some input, which could be a digit or a letter, that image is fed into the beginning of the network, where the start of the network, just like in Fukushima's proposals, just like in biological vision, are very simple representations like edges. As we move deeper into the network begins to create more complex representations by combining those edges together into corners and simple shapes. And then at the highest levels of the network has representations of digits in general. So it begins to be able to capture the shape of what a 3 looks like and how a 3 is different from a 2 and a 2 is different from an 8. The idea here with Learning15m is that you're not explicitly telling the network what it should be looking for. You're just feeding it lots of examples and it figures it out for itself. That's the deep learning principle in general. So in deep learning, what we end up doing is not engineering basic features. We're not telling a network how to identify specific edges or how to combine those edges into the parts of letters of the alphabet or digits. We're simply building a model, and the feature engineering happens automatically. We'll contrast that with traditional machine learning in a second. After this zip code application that Jan LeCun and his team developed, there was an artificial intelligence, a deep learning winter. People became skeptical that there were many other approaches for which stacking artificial neurons into these deep learning networks would be useful. And part of this was fueled by this parallel machine vision path, where people were spending a lot of time in academic circles and in commercial circles on engineering features, so on engineering the edges and the simple aspects of visual stimuli. And that line of research through the late 90s and the 2000s was getting a lot of the success. This kind of approach, where you're spending the vast majority of your time engineering features as opposed to actually building the statistical model with those engineered features, is best exemplified by this paper from Viola and Jones in 2001. So Viola and Jones set out to recognize faces. To do that, they created these features, these rectangular boxes, you see two examples of them here, which were able to identify changes in contrast in the image, darkness and lightness, that tended to exemplify faces. So you can see here that the basis of Viola and Jones' research, which is the whole basis of this parallel stream of machine vision applications, was focused on engineering features, and the features that they came up with here were these rectangles. And this approach worked well. So this approach was actually commercialized into digital cameras, and so in the mid-2000s, when we started to have cameras that could recognize faces and automatically focus on those, that was a product of this kind of research. And so it seemed like maybe this machine learning, feature engineering focused approach was all we would need, and that deep learning was no longer relevant. In the background, however, there were a few labs that continued to press on with the deep learning approach. So with the brown strand here. So those labs were primarily the universities of Toronto, Montreal, and Alberta, as well as Jan LeCun still at New York University. And as they were making refinements to their theoretical approach, there were other changes happening in the world, huge increases in data, processing power improvements that enabled the artificial neural networks to improve to a point. By 2012, artificial neural network research had advanced enough that this AlexNet, put together by Alex Krzyzewski, Jeff Hinton, and colleagues at the University of Toronto, was able to finally outperform the kind of feature engineering approach here. So, although many of their ideas was similar to Fukushima's idea in 1980 and to Learning15m in the 1990s, they had the advantage of much larger training data sets. They had the advantage of much more powerful CPUs, and they had the idea to use GPUs as well. So GPUs are able to parallelize a lot of the matrix algebra that we're doing inside deep learning artificial neural networks. And so the combination of data and processing power and a few more layers of depth in their network enabled AlexNet to greatly outperform any of the other machine learning approaches for machine vision at that time. So the particular competition that they made a splash in was called the ImageNet Large-Scale Vision Recognition Competition. We'll talk about the ImageNet data set in detail later on. Essentially, it's millions and millions of images categorized into thousands of categories. And as soon as AlexNet had won that competition, everyone took notice. They reduced error rates in that competition by a tremendous amount. And since 2012, all of the winning approaches have been deep learning approaches from this kind of school of thought, as opposed to the feature engineering school of thought. And so that's what's brought us to today, such that we now see deep learning applications everywhere. Like Learning15m that we were looking at earlier, we will also build AlexNet in these live lessons. So you'll get to see the power of this structure as well, and you'll see how stacking artificial neural networks deeper allows us to have more nuanced representations learned. Alongside all of the success in machine vision, other techniques like natural language processing techniques had similar kinds of timelines, with a winter until up till about 2012, when deep learning approaches started crushing feature engineering approaches in natural language tasks as well. Since 2012, deep learning has made its way into countless everyday applications. So in machine vision, like we've been describing, deep learning algorithms are being used in Tesla's self-driving cars and Facebook's face tagging suggestions. In natural language processing, deep learning is used in voice recognition that powers Apple's Siri, Amazon's Echo, etc. And it's also used in machine translation and online search. In 2012, Google was using deep learning in none of their projects, and it's used in more than 300 of their projects today. Deep learning has even been making front-page headlines for surpassing human-level performance on a slew of tasks, from Atari video games through to the complex board game Go.